Hi, I'm Ladislav Kavan, and I'll be talking about environment scale fabrication, replicating outdoor climbing experiences. This is joint work with Emily Whiting, Nada Ove, Leanne Makatura, Christos Mousas, and Zhenyu Xu. The idea for this project was born when Emily and I were postdocs in Switzerland, and one hobby we have in common is rock climbing. Climbing is becoming an increasingly popular sport, and that's partly thanks to indoor climbing gyms, which make climbing accessible to a wide range of people. Climbing has been also officially approved for the 2020 Olympic Games in Tokyo. However, there is a big difference between climbing in an indoor gym and on a real rock, and we can ask whether it's possible to make these two experiences more similar. Why would we want to do that? Well, some well-known rock formations are prohibited for climbing. The delicate arch in Utah, which you can see in this picture, actually has been climbed, but it generated a lot of controversy and resulted in new, stricter regulations of climbing access for the entire Arches National Park. Some other rocks can be climbed legally, but it's barely within human possibilities. Here we can see a very famous route in Germany called Action Directe. This route has been climbed only by about a dozen of elite climbers and has some interesting stories attached to it. The first ascent of Action Directe was done by Wolfgang Gulich in 1991, and when he was training for this route, he invented the campus board, which is now a standard training tool. More recently, a Romanian climber, Matthias Luzan, has been very motivated to join the elite club of people who managed to climb this very difficult route. And because he lives in Romania, he decided to build an indoor replica of the Action Director route in his local climbing gym so he can train on it without traveling to Germany. This project took several years and required remarkable craftsmanship to complete. We are not elite climbers, not even remotely. We are computer scientists. So we approach the route replication problem from an engineering perspective. We thought it might be promising to use the 3D printing technology to help us replicate rock climbing routes. But the first problem you immediately run into is that 3D printers have only limited volume. If you want to fabricate larger objects, there are several possibilities. You can use larger hardware, which is capable of printing entire buildings. But this takes a whole lot of, but this takes a while and uses a lot of material. Second, there are clever software solutions, which essentially split a larger object into smaller pieces, which nicely fit together. And that works well for mid-sized objects, such as a chair. And finally, there is the option of doing strategic prints, replicating only the relevant aspects of the input object. And that's the option we chose to pursue. But what strategic means in our context? Well, on our difficult rock wall, there are only a few good features the climber can grasp or stand on. The body senses the external forces, the gravity and the contact forces, and the motor system sends signals to activate the muscles in such a way the climber can move up. And we would like to recreate precisely this sensory motor experience. We approach the problem from a geometric perspective. Specifically, we have identified the following three geometric aspects. First, we want to replicate the same spatial configuration of the handholds and the footholds, the global geometry of the climb, if you will. Second, we also need to preserve the details of the contact regions, which determine the hand grasp and foot placement, matching the local geometry. And finally, we also need to match the friction characteristics of the rock, microgeometry, if you will. Now, to make the problem tractable, we introduce some simplifying assumptions. We assume only flat vertical walls, deferring overhanging or inclined climbs to future work, and we also replicate only part of the entire route, the hardest sequence of moves known as the crux. Here is an overview of how our system works. First, we reconstruct the 3D geometry of the crux region using multi-view stereo. Next, we create small-scale 3D models of the individual climbing holds. Then we fabricate these holds, turn them into actual physical pieces, which can be mounted in an indoor gym. And the last step is figuring out how and where exactly to place these fabricated pieces at a man-made wall, taking into account the constraints of our indoor climbing gym. So let me explain each of these steps in more detail, starting with the acquisition part. Given an outdoor route, we first climb it and set up a top rope anchor. This allows us to take a lot of photos of the crux region. We take between 2 to 500 photographs from all possible angles to capture all of the details of the rock. We feed these photos into a multi-view stereo software, which creates a pretty detailed 3D reconstruction of the rock wall. And we combine this with a video capturing a climber ascending the route, which we use to identify the contact regions, the key rock features the climber used during an ascent. We assume the climbing motion can be broken down in a sequence of almost static poses. In each of these poses, the hands and the feet of the climber are in contact with some of the rock features, and we want to identify their exact locations in the 3D reconstruction. So how can we do this? First, we can use multi-view stereo to find the parameters of the camera that was recording the video of the climber in action. And this allows us to project the locations of the climber's hands and feet from a video frame to the reconstructed 3D geometry. But from the video, we can get even more. We can run a motion capture algorithm to approximate the skeletal poses of the climber. And in each of the poses, we are looking for rock features which the climber is grasping and standing on. And we locate all of these contact regions along with approximate direction of the contact force between the climber's body and the rock. Once we have found all of the contact regions, the next task is to turn them into nice 3D shapes similar to standard indoor climbing holds. To do this, we define two boundaries. We call them inner and outer boundaries. The inner boundary, the green curve, encloses the contact region in red. The contact region is frozen. We don't want to modify it because it captures the key details of the rock we are trying to replicate. The outer boundary in blue is where we cut off the hold from the 3D rock wall geometry. And between the inner and outer boundaries, we create a smooth transition to get a nice shape which is suitable for fabrication, making sure we don't create any new features which could be used for climbing, for grasping. A fabrication is not completely straightforward because the resulting holds must be very durable. It must be able to withstand the full body weight of a climber applied from different angles. Also, the surface texture should mimic the friction properties of the rock. We tried several possibilities and found the following fabrication process worked the best. We start by cutting the shape of the hold from a high-density foam using a CNC router. Then we create a silicone mold, and after it has cured, we fill it with casting resin, which gives us a nice solid piece similar to standard indoor climbing holds, but replicating the 3D geometry of the outdoor route. When the piece is finished, we drill a hole in it where we put a bolt, attaching the piece to the indoor climbing wall. And this leads us to the next phase, where we need to decide where exactly do we want to place our pieces in the indoor wall. The goal is to replicate the spatial configuration of the outdoor route while using a fixed, pre-existing set of T-nut fasteners where the pieces can be mounted. Those are these little blue dots. We are not allowed to drill in the indoor wall to insert more T-nuts. So instead, what we do the following. First, we create a model of our indoor gym. We do multi-view stereo reconstruction, just like we did with the actual rock walls. And then we locate the 3D positions of all of the T-nuts and reduce the problem to 2 dimensions, because we assumed we are replicating only a flat vertical wall. For each of the fabricated pieces, we mark the ideal location where we would like to drill the hole for the bolt, typically close to the center of mass of the piece, because drilling a hole close to the boundary would reduce durability. However, we are free to pick where exactly we position the replica in an indoor gym wall, within the region we are all to use, of course. So this means we have 2 degrees of freedom, global X and Y translation within given bounds. And we want to find such a translation vector of the entire set of pieces that matches the best with the pre-installed T-nuts in the indoor wall. This can be formulated as an optimization problem, and I'll refer you to the paper for the technical details, but let me just give away the key idea. The key idea is local global alternation. It's an algorithm similar to k-means clustering, alternating between optimizing for the best 2-dimensional translation vector and finding the closest T-nut for each piece. So we run this optimization process from different starting points, as you can see visualized here, to increase our chances of finding a global optimal. At the end, we pick the best solution and print the final configuration of our pieces, which will serve as a blueprint to build our indoor replica. So finally, we can mount our fabricated pieces in the indoor gym. Our pieces are these ones, the white ones. And the next step is the fun part, is to actually climb it. And note that the climber is allowed to use only our holds, only the white ones. Our route can naturally coexist with regular man-made indoor routes. So we can be asking, how does climbing of the replica compare to climbing of the real rock? Let's take a look. In this video, we put side by side recordings of the same climber scaling the outdoor route, the original one, and its indoor replica. This replica was built specifically for this climber. You can see the moves are not exactly identical, but they are fairly similar. To the end of the cracks. Let me play this one more time. By the way, one advantage of training with an indoor replica is that it spares the real rock from deterioration. This video shows another climber on the same route, again comparing the original outdoor route and its replica. Now, this climber used a slightly different footwork on the outdoor route. So the moves are a little bit different, but this could be improved by fabricating additional footholds for this particular climber. We replicated yet another route called Pilgrimage from southern Utah. It's a completely different type of rock. It's a sandstone, but it has the same difficulty rating, 512A. And this move is the crux. These guys make it look easy, but it's really hard. Trust me, I tried. Note that here we are comparing two different climbers because the original rock route is in Utah, whereas the replica was built in an indoor gym at New Hampshire, more than 2,000 miles away. Let me play this one more time. So we are quite excited about this, but of course there are still a lot of limitations in our current system. First, we made the simplifying assumption of focusing only on vertical walls with small, sharp features. In the future, we would like to extend this to model overhanging or inclined routes, possibly using climbing volumes to model larger rock features economically. Second, we assume that a lead climber can ascend the route so we can get the photos for the 3D reconstruction. While this may not be always possible or allowed, such as with the Delicate Arch in Utah. So what we like to explore instead is drone photography without any person actually physically touching the real rock. And so far, we have used only one climber's ascent to create our replica. But of course, more general and better replicas could be produced by using videos of multiple climbers ascending the same route and putting all of the contact regions together. And finally, while we focused on rock climbing only in this work, we believe that the idea of environmental scale fabrication could be used in many other contexts. For example, we want to replicate a crime scene where the spatial configuration of the evidence may contain important clues. Or maybe want to replicate a historical site, for example, prehistoric settlement or cave dwelling. And each of these problems will, of course, have its own challenges, but will have to be addressed properly. So that's the end of my talk. I would be happy to answer any questions you may have. Thank you.